discussing Carlo Sferrazza's presentation he gave at Berkeley a few months ago about humanoid robot learning, foundation models, and particularly omni-retarget, which is a very interesting approach towards learning from video. I think Carlo is on a path that we here at Orange Capital Partners are very keen on, and that is a path of robot learning from scale, finding a way to apply the bitter lesson to robot learning and then bridge that into simulation and then go from there and circle back to the real world. He's not fully, it's his presentation, obviously. We're reacting on it because we have a lot of thoughts that overlap, and the purpose of these types of episodes is it's not just to give people a sense for what it feels like to run a hedge fund, which is the main purpose of our podcast. But these types of episodes, when we actually discuss researchers and their approach, it's more for us also to draw the lines where we stand relative to the research community and, of course, what we think is actually feasible in terms of transitioning from science into technology and making these things commercially scalable. This is a Not Even Run podcast. It's May 31st, 2026. This is Krimdelko. For the year, we're up 90 basis points. The market is up 10.7%. We're underperforming by 9.8%. So Carlo Sferrazza is a postdoc with Peter Abil, just recently got appointed a assistant professor position at UT Austin. His work is in the realm of computer vision, robot learning, humanoid robot learning, scalable robot learning, general models. Like in that sphere, I think what's interesting about this particular presentation, the links in the show notes, is that it's tackling some of the most important issues we believe need to be tackled with robot learning. And one is learning from video. That to us is the absolute crucial point that needs to be solved in order to have similar breakthroughs, if not even more breakthroughs in robotics than we had in language. Now, just let me sort of interloop here, give a little bit of background on the situation, what's happening in AI. In general, for about 10 years, so from about 2012 to 2022, the consensus in the AI community was that computer vision will drive real-world AI and bring us towards something that maybe we can call artificial general intelligence. And the idea was that that's how evolution did it, right? Evolution started, there is the blink of an eye. I think there's a book that Fei-Fei Li and others propagated saying that when biological evolution developed vision, that we had a Cambrian explosion of our species, and that created a much more richer world. And we have a similar situation now with artificial intelligence. Now, this idea was kind of intercepted with the success of large language models. And I think since 2023, since the launch of ChatGPT 4, I believe, or whenever that success was, and triggered this huge investment in large language models and the subsequent really rise of agentic models, workflows, software development. So anything that is languageable is being taken over by AI. So there's a little bit of I would say almost there's a large language model summer and somewhat of a robot spring. It's not a winter. I think people have their hopes high. Tesla shareholders, they hope that Optimus can work. Figure shareholders believe that 30-40 billion valuation is justified and so on. So I would say it's a robot spring, but clearly the big work, the big ideas, the big investments are being made in the large language model space, particularly in the agentic, which is sort of, kind of like a cousin of large language models. But let's just, for the simplicity of this episode, call it the digital space. Now back to Sferrazza. What he's talking about in Omni Retarget, which is one of the papers he's presenting, is the what's called kinetic retargeting. Kinetic retargeting, I believe that's the word. So you're looking at a video of a human, lifting boxes, screwing screws, whatever, and then you're retargeting that to a human robot. You're doing that with a sort of mesh architecture. So you have waypoints and relationships between limbs and fingers and your body and the object, and you're kind of exploiting that locality and symmetry, which is given by the physical world. Like the physical world has a lot of priors, right? Yes, we're doing end-to-end learning, but even us humans, when I drop you in the jungle and you're supposed to figure out how to proceed, or when Robinson Crusoe got stranded on the island, there was clearly from scratch one-shot learning, but there was still a lot of inductive bias. Like, for example, he had his limbs and his size and his and I'm just talking about geometry here and physics, not even the biological bias, but he can't, I don't know, he just can't reach more than whatever his limbs are and things like that. So he's not going to learn how to reach a bird with his hand unless he finds a way to attack the bird and live with the constraints of his size. I guess again, this is what Sferrazza is talking about in a more formal way, is that we have locality with our body, and we have locality also with the environment, and that can be exploited. And actually, we can use transformer architectures. He separates the talk into 4 segments. One is data, one is architectures, one is algorithms, and one is simulation. So I'm just going to follow that kind of loosely. What he means with data is, again, learning from video through kinematic retargeting. The architecture is applying something like a transformer architecture to exploit locality. Like if you think about the attention mechanism, if you think about the structure in language, you have similar structure in the real world. It's a lot more diverse, it's a lot more random, but there's still structure. Like a bird is not going to fly from below. Most likely it's going to come from the top. Like there's a lot of things, again, we have a lot of priors that we can work with. And the idea, of course, is to exploit those priors within an end-to-end network, so within the bits of lesson context. So we don't want to actually, we don't want to put any priors in there that are sort of human-generated or our own thoughts, like following, the bits of lessons, main lesson, which is, let's not try to build AI that thinks the way we think thinking works. Let it just learn on its own. So I think we here at Orange Capital Partners are incredibly excited about the idea that we can use the pre-trained, mid-trained, fine-tuned pipeline that has been used for large language models also for robots. And I think Sferrazza here is, at the end, he's saying a few things that might actually not go into that direction, but then his presentation is supporting that. So I would have to double check with him. But my point is, I think that the most interesting idea in robot learning is how to learn from human videos. And by the way, that's why we have the humanoid form factor. It's not because the world is designed for humans. It's not because we want them to look nice when they work in our house. I mean, those are real arguments, and you can say they're nice to have, but the main reason is because we want to learn from humans. We have one robot, a biological thing with limbs and hands and moving around in the world and actually pursuing goals, acquiring skills, executing tasks. Why don't we learn from that robot? And that robot's called human. So, and we have actually internet scale data, based just YouTube and all that other stuff. Now, there is also the data that comes from let's say specifically trained human teleoperation, and I would put that in the sort of mid-train bucket, right? So I think our approach here at Orange Capital Partners, the way we think about the space is the pre-train happens unsupervised, very loose. There's no bias whatsoever. We just, I mean, there's no bias in the way we structure the models. Of course, there's a bias in the architecture we use. So whether we use a transformer architecture or some sort of diffusion architecture, I mean that of course is a huge decision that we have to make. And we here at Orange Capital Partners, since we're not actually building those models, we're only investing. I guess the best is to hedge our bets here. But the point is, again, large-scale unsupervised learning from video data with kinetic retargeting to have a body of knowledge embedded in the robots, in the robots. So the robots have a certain body of knowledge that they can draw from, very similar to large language models. And then the mid-training happens, and there's a couple of things that Sferrazza talks about here. One is the I believe he calls it dagger. Now again, I could be butchering the actual names of the models, but I'm just going to talk about the concepts. So the concept is that you have an offline reinforcement learning database, which is kind of like, think about it like a massive database of human actions that solve problems. Again, actually not even task specific. And you can then have task specific data mixed with that data set, and then train the now pre-trained robot on specific skills, how to actually screw this screw, how to actually, lift the boxes. Sferrazza then is also working on some sort of randomization concept, which just means that you want to be able to adapt to the environment. And that happens by, think about yourself, like you've learned how to jump over obstacles, but when the obstacles change, you can still jump over them. You just adapt your policy to the height, the size, the width, and all that. And the same goal here. And they're doing that with, I guess the way I understand it is you have a trajectory which is mapped one-to-one from, let's say, the most likely action chunk that you're mapping your specific situation with. But then you have a leeway, so you have some distribution around that action chunk that allows you to adjust to the actual space. And you could do that maybe, again, with offline reinforcement learning or even online reinforcement learning, where the robot learns on the fly how to do it. The same like a human. You just try a few times, you might fail, and then you figure it out. So that's sort of the idea. Again, how do we scale the pre-training and mid-training phase? How do we increase speed of learning, which basically comes down to parallelism. I think anything in AI has to be parallelizable, otherwise it's not scalable. We simply don't have the energy, the time, and the bitter lesson doesn't work without parallelism. So we need to find ways to parallelize almost any process. Otherwise, it's not going to be scalable. At least not scalable in the sort of way we're used to. We can still scale, of course, without parallelism, but the real superhuman intelligence is the real this what we call AGI, or the kind of intelligence that we're all really believe in, is only possible through parallelization, because it's, in the end, it's just iteration, try and error at scale, and then finding intelligent ways to discriminate those try and errors, to have the counterfactuals point towards a better solution for certain problems. I think I want to say a few things now. Again, some of them overlap with Sferrazza, some of them are our own thoughts, and that pertains to the way we see the space evolve from here, in particular as it relates to simulation. Because we believe that world models actually are going to be the crucial piece of the puzzle that will enable a massive robot revolution, much, much bigger than what we're seeing now in large language models. Like, to the point where we can not just execute human tasks, but execute new tasks and most importantly, also send robots, let's say, to space or to places that humans barely can go, and the data collection would be impossible. So it's about world models, and what we think is going to happen, or has to happen, or the right approach here is that we actually start with the robot data. So we have robots in the field, and one example would be the Tesla robotaxi. So that's one robot in the field at scale, hopefully this year. And when I say scale, real scale, tens of thousands. And then from that data, you build a world model. So now you have real world data. And what I mean by that is states and transitions with actuators, that data. So we have states, and it's all camera based. So we have the semantics of the camera, and actually Sferrazza mentions that we don't want to have, a radar, LiDAR, none of that. We want to actually have pixels, because pixels give us the context, and that's very important. Because with the context, we can then exploit, for example, local symmetries and all those kinds of things. I mean, we can, let's say, steps go up, the steps are all the same. So we don't need to learn every step. We can kind of extrapolate, and then we see a different step, and then we adjust, like things like we don't have to always, every time we go one step up, retrain from scratch, or go through the model, go to the forward pass. We can use the semantics, and that for that we need pixels. So we have those pixels, we have the robot data. Now, what exactly we collect as far as robots are concerned, proprioception, touch, things like that. Let's leave that for a second, that because that's an open research question. But let's just stick with, again, if we learn from video, what we really only have is basically geometry and semantics and all the stuff that Sferrazza talks about, the local symmetries of the body, the geometry, and things like that. So we have that. Then maybe in mid-training we can add proprioception data and other data to the robot. But once the robot is deployed, here's the key. This is what I'm trying to say here. Once the robots are deployed, let's say we have tens of thousands of humanoid robots working in factories. We then pull that data back into a world model and actually train the world model based on that robot data, and then use the world model, which is embedded in the real world through real robot data. And by the way, it could also be human data, but since we now have real robots, we're kind of bridging the gap between humans and world model through robots, because the robots give us all the data. It's much harder, let's say, we could put chips on a human and stuff, but we don't want to go there. So we already have, the robot is a data collection machine. So I guess what I'm saying is this early fleet of robots is not just going to execute tasks for us. It's a data collection machine. The reason we want to launch all these robots is to have a fleet of data collection machines. That's the key, to build the world models that we then can use to really, bootstrap. Maybe the analogy would be that the first fleet of robots would be like the first airplanes after the Wright brothers, World War I type airplanes. And then we want to transition to jet engines and rockets. And that happens through world models, which are embedded in the real world. And then we can use a lot of tools that we have. I mean, Gaussian splatting would be one, but there's many other simulation tools. We have also sort of legacy simulation tools, physics simulation, all that kind of stuff. We can actually improve those tools also with the real world data that we have. So, I hope it gets clear that the flywheel starts to work here. And then once we have those world models, again, embedded in the real world with real physics, then we can train robots at a much faster scale. Again, parallelism is key here. And then bring them back to the real world, learn from that, and boot. So and just keep going. So again, the first batch of robots, this first fleet is actually mainly a data collection world model bootstrapping fleet. And it will, of course, have to have commercial success, because we won't have these things deployed at scale unless they are a commercial success. But the fundamental idea behind launching these things is to have a data collection. And some companies, let's say Meta, is trying to do it with the glasses. So they're they're trying to put glasses on humans and collect data. So people are certainly not blind to the idea, but I think the real breakthrough is when we have a commercial application. So it's kind of like the Tesla FSD business model, where we have a commercial product, FSD, launched in the real world with real customers. We then collect data through shadow mode and things along those lines to then feed back into a simulation engine and then improve the model iteratively. So that what works for self-driving is also going to work for robots. This is our view, and this is maybe where we differ a little bit with Sferrazza. I'm not sure. I haven't been able to speak to him, personally, and I would love to, and I would definitely also love to meet him at CVPR, although it looks like we're not going to be able to physically be present there. But these are the kinds of things we're looking for at CVPR, and I think this presentation, I already mentioned in the previous episode, our preview of CVPR, and I think this is a very good example of a presentation you want to pay attention to, and then extrapolate from there. Go around CVPR and find, either supporting materials, papers, talks, or contradicting, and learn from there. Thank you.